Hi, it's Terry Denery of the MathWorks. So let me hit the run button on this. But what we're looking at here, and what this video is about, is how do we take that control that we've developed in our previous video and bring it to the real world, bring it to hardware. Okay, and um, and so in kind of presenting this video, we're going to talk a little bit about why does the model look the way it does, and what are these colors about. In a way, that's what this video is about as well. Okay, and I'll just say that in bringing a control to the real world, it means getting that algorithm um, expressed in code that can run optimally on an embedded processor. Okay, and that embedded processor will be then connected into the instrumentation of the system that it will be controlling. Okay, and it's going to get into some concepts like fixed step versus variable time step. And I'll just kind of say quickly that when you're doing hardware implementations, you have no choice but to run in fixed time step, as signals which will be generated by your hardware um, can only deliver that at a fixed time step. And so we'll kind of get into that a little bit. Um, Now, with regard to the colors, well, all computers essentially operate with discrete signals. That's the general nature of how computers work. But when we run things on our laptops and use these great tools like Simulink, which use variable time step integrators and things like that, we can create the illusion as if things are running kind of continuously. Okay, but anyways, as we get into embedded processors, we're very cognizant and we're very deliberate about operating with discrete rates, and you'll see that our controller, is shown by this red block right here, is generating signals that are going to be delivered at a rate of 1/1000th of a second. Okay, meaning that this algorithm is going to update that signal at a rate of 1,000 hertz. Okay, and for mechanical systems, that's pretty typical and very useful. All right. So now let's just kind of take a look at kind of what's happening with this. And I think it's just about done. I think I'll just kind of rerun that motion. And so everything's looking good, that this implementation seems to work. I think I'll put this down. We'll take a look at kind of our measurements. We'll see again, the blue line is right on top of the yellow line, meaning that the response of the system is precisely what we commanded it to be with the yellow line. All right, so they're essentially indistinguishable. All right, and our voltages and currents look real good, just like they did in our previous simulation. I think I will take you to a little bit of a zoomed in look here. And I like this. I see this little chatter here. Okay, and what that tells me is that my feedback controller is doing a really good job. It's responsible for that little bit of chatter. And what we introduced here is some noise that the system will be subject to, and that the PID is the thing that can kind of deal with the uncertainty of noise that's being used to test our algorithm. So anyways, all things are looking pretty good with regard to this. I think I will just kind of zoom in and really make my point, that the controller has this kind of interesting representation now, precisely kind of look at the corners with the little diagonal, indicators, right? And so if you're familiar with MathWorks um, and Simulink, and especially if you do a lot of stuff with like embedded coder, you probably understand that that's what we call a model reference. And what that means is I can click on this button right here, and it's going to open up a model file which contains the controller, so that this controller is participating in the overall simulation via reference to this other file, this other Simulink file. Okay, and there's a lot of really great advantages of it, and I'll kind of keep it simple, but I'll certainly say that as you divide up the work of creating a system like this, you really want to kind of hand off some things to the software development team and allow them to just kind of move forward without too much interaction with the other groups. And so it means that there's a nice negotiation that takes place very early And so the mechanics and the electronics folks, they kind of know the sensors they're using, and they understand the PWM rates at which they want to, kind of drive voltage signals and that sort of thing. And so they absolutely have a concept of discrete rates, that their instrumentation very much is defined by discrete rates. And software people, of course, are very interested in things like rates, but they're also interested in things like data types. Okay, and so for this controller, we're kind of keeping it very basic, and you see we're just using a double, but I do want to show the full capability of Simulink through embedded coder to pretty much represent whatever data type you might need. Okay, and so I'll just say that these input and output blocks are kind of the nice negotiation between the software teams and the hardware teams to really define the boundaries which will allow them to kind of operate and do what they need to do. And all they need to do is make sure that they deliver these signals per the specification that was um, mutually negotiated upon by them and the other members of the team. Okay, now the other thing that's really special about model reference is that it is its own model, and it means that you can choose your own solver, right? And we saw that this is operating discretely, and I want to just kind of explain what that means. And it certainly means that it's fixed time step. So anything that kind of connects to hardware, it'll have no choice but to run in fixed time step. That the alternative would be, of course, variable time step methods. And I'll just say it this way: the variable time step methods are based on the idea of try again. Okay, and what they mean by that is, well, try it with this sample time step, and then after the calculation's been formed, check and see if it's converged properly, right? And these methods are very good at actually understanding if it's numerically converged based on some, I'll say, accuracy settings that you may have chosen. But anyways, if it does not, the idea is go back, and try again with a smaller delta t, and continue reducing the delta t until you get a update of your system that does satisfy your accuracy requirements. All right. And so then the other thing I do want to point out is that, Simulink works by choosing solvers, all right? And there's all these fancy, kind of numerical integration solvers based on like Rungokutta and things like that. And that in general, when you create a controller, you kind of like to use this one. And we call it discrete, continuous states. And kind of what that means is that, well, first of all, you aren't going to use our fancy solvers, but what it also means is that what you see is kind of what you get. Everything that is kind of happening mathematically in that algorithm that's represented by this controller, it's very much self-contained in a description point of view of all the things that we're seeing here. We're using a PID discrete controller, and what that mostly means is that the derivative is calculated based on, well, I don't want to dive too deep into that, but based on very simple formulations that they're really very much represented inside this block. There's probably a way to look under and see all that kind of stuff, but that's not what I'm most concerned about. Um, and that, but what I needed to do to kind of get this so it runs discretely with no continuous states was I needed to actually move to the equations of motion for the system. That and I'll just kind of show what it is at this point. But it's basically taking kind of our commanded input, how we want it to move, and that's essentially telling the motor what I want its acceleration, velocity, and position to look like. And it then calculates what the torque will be. And it does it by direct access into the equations in motion, which we see expressed here in this MATLAB function, ultimately used to calculate this torque Z for the motor. Okay, and yeah, and it's a little bit hard to explain, what these integrators are about. But I'll just say that to avoid kind of a tricky singularity, a nice little trick was to just calculate velocities and identify positional updates by simple numerical integrators that are, again, employing this very simple kind of discrete method. And These I think are forward Euler and essentially means I know what the derivatives are. I multiply it by my fixed time step delta t, and I update our previous value for those signals by that product. All right. So, anyways, hopefully I've made my point that the math is fully contained and it's reasonably simple. All right. And so that's always a good thing for controls. And I think I'll just kind of get a little bit more specific on that point by going into our code generation report. So I've already generated the code for this, and I'm going to bring you to our static code metrics. And we'll see that this controller, the entire thing contained in this entire model reference, it's a sum total of 210 lines of code. So we're seeing that right there. And then I want to show you what the controller is, and almost all of it's contained, well, I'd say most of it's contained in this motion controller step function, right? And what we're going to see here is most of the stuff that was showing up in that MATLAB function is reproduced, but of course in C this time. And that, somewhere down here near the bottom that it identifies, yeah, right there, ZIDX15. All right, and it's mostly my familiarity with this model, but it's the point I wanted to make is that the job of this is to calculate, where is it? There it is the torque. All right, and so there's your ZIDX15 is your feed forward piece, essentially the ideal torque based on your intended motion, and then the PID we're kind of seeing included in that too. Right, and so that's your essentially your torque that gets implemented. All right, and to just kind of again emphasize how important it is to get to the equations of motion to do this, I do want to show kind of the alternative, and we could do it with SimScape Multibody. And SimScape Multibody is a superb tool, but it's a tool that ultimately will pack the the numerical method of SimScape Multibody into the controller. And so I want to show what that version of the controller looks like in this model. Oops, click on that right there. All right, and we'll see its version of a model reference. And again, we know it's SimScape Multibody because we see the transform blocks, we see joint blocks and body blocks and all kinds of stuff. And looks like it's still kind of loading in. And let's see, I guess to get to the coder, maybe I need to do this. There it is, embedded coder. Oh, there it was. I must have been blind. Okay. All right, and let's open up the report and go to the static code metrics because again, I've already generated this code. And you'll see that it's 4,690 lines of code, meaning it's more than 20 times bigger code base than we had with our discrete no continuous states controller. We'll see lots and lots of functions, all these blue things right here. And we do have links to look at it. And I want to bring it all the way down to the mechanical motion controller step function, which we see here. And I'll just say that you're seeing all kinds of references into all kinds of functions that, I would probably want to figure out what they are. And I'll just say that I'm slightly intimidated by that. So anyways, hopefully I made my case that it is good to get to the equations of motion. And I think I'll just kind of finish this video by going back to this, all right? And the next video will be, well, how do you get this, all right? And it turns out that it's going to come from the same origin, which is the SimWise file, and we'll see a new tool that we'll describe in the next video called Motion Genesis, which can take that same mechanical description and using kind of symbolic methods generate the the system equations that describe the dynamics of this mechanism. And in describing that, we can essentially solve for the torque. And then that's exactly what we did. So anyways, a lot of really, really great capability there and a lot of really, really great tools that we do have access to do some very remarkable things. So anyways, um, we'll show that in our next video. And thank you for attending this one. I hope you keep on watching.